Okay, good morning everybody. Welcome to the last MZV or EMZV lecture. Thanks Matthias for the introduction. So the point where we stopped yesterday was that I had defined what elliptic multiple zeta values were, and one of the questions after the lecture underlined the point that these objects, despite the fact being called values, are not numbers. So if it comes to these numbers, and I will continue to call them numbers, then we have seemingly a lot more structure than we had for the actual multiple zeta values numbers, whose structure we had been exploring looking at the integral representation. In particular, if you have a function instead of a number, of course you can write down differential equations or do something with the geometric parameter or modular parameter tau, and that will be the main topic of today's lecture. So let us explore the space of elliptic multiple zeta values, keeping in mind that these objects are not values, but actually functions of the modular parameter. So I had defined omega of n1 to nr. This is a little dim here. Oh. Okay. I had defined omega of n1 to nr and added the tau explicitly in order to make sure that it's clear we are having a function here. And what one does, one can expand this function in a power series in Q. Q was defined as the exponential of 2 pi I tau. That is, conveniently, one does write the expansion in Q. It goes also by the name of Q expansion. Despite this fact, one usually notes a tau for the multiple zeta value. So tau and Q, if it comes to naming variables, are equivalent here. And the structure is as follows. One can show that there is a thing, omega 0, which is called the constant term. And in addition, there is an infinite sum, k equal 1 to infinity of, with a coefficient ck of n1 to nr q to the k. This expansion can be retrieved for any multiple zeta value based on the fact that the multiple zeta values are functions or iterated integrals over a particular set of differentials. These were these differential forms f, lowercase f, d psi we had the last time. So the last time I had asked the question, what is a proper genus 1 generalization of the dt over t minus a differential form? And the answer was that there is a generating series, the Kronecker series, which I named capital F or capital omega if I want the doubly periodic version. And the expansion coefficients in one of the variables, they would deliver an infinite set of differential forms, which in a certain sense are canonical differential forms on a genus 1 surface. Now, these functions Fn, they will bear an echo of the doubly periodic correction I had to introduce. In fact, one can actually relate them to functions gn, which are more appropriate for our purpose. At the very end of last lecture, I had written down an integral representation for the omega a's, and I made a comment that we are talking about elliptic multiple zeta values defined with respect to the A cycle of the fundamental domain. In particular, this meant that the iterated integral will have real values only. So there was a 0 less equal ti less equal ti or zi, I can't remember, plus 1 less than equal to 1. And I assumed all those iterated variables to be real. In the same sense, one can look at a real version or a projection on the real line of these functions fn of z and tau. And there is a combinatorial way of writing that down, whose form I'd like to note. So there is a sum from 0 to n, and then you divide, or you get a sum over all different n's over k. Let me write it down first. So in short, you can get these f's of a certain degree n by summing with the prefactor with a couple of 2 pi i's over all the g's. Nevertheless, in here, there's again this ratio which already appeared up in the doubly periodic completion of the function f. So there is imaginary part of z over imaginary part of tau. And if you're looking at variables which are real, then we can completely forget about this prefactor, and the only contribution we will actually get for the class of functions we'll be looking at is precisely that for z real, we'll get that fn of z and tau is equal to g n of z and tau. So you can forget about that formula here and simply call these g. The reason I'm still mentioning that is that when these objects were investigated closer, there was a lot of discussion what kind of iterated integrals one actually should look at, whether one should put the iterated version on the real line and whether this would contain all the information necessary to explore the algebra of elliptic multiple zeta values. The answer is yes, they are sufficient, and you can define a so-called homotopy completion, and the homotopy completion will tell you how to relate the g's to the f's and how to find an integration path which is not the real on the real line. So in short, there exists a perfectly valid theory. The paper from Andrei Levin is called Elliptic Polylogarithms and Analytic Theory. So everything works out beautifully, but for today's lecture, I would like to stick to the real line, and thus I can use the functions g. The reason I'm introducing these functions, they have a very nicely accessible Q expansion. And the goal here was to write the elliptic multiple zeta value as a function of tau in terms of this Q expansion. So we better note what the Q expansion actually is. So let me write down what that is. G of 1 of z and tau is pi times cotangent of z, the cotangent that is in the same way as for f1. I mentioned last time, yesterday, that we have the pole we want in the differential form. Here it is the cotangent which actually carries the pole. In the limit z goes to 0, that will behave like a 1 over z pole. And then there is a Q expansion which comes along with that 4 pi m equal 1 to infinity, and then some sine function 2 pi m z, and another sum n equal 1 to infinity, and then we have q to the power m n. That's what we want. And then there is 2 other versions, so you have to distinguish between even and odd, k equal 2, 4, and 6. And it will have something like a zeta function k in the beginning. And then there is again a large sum 2 pi I over k minus 1 factorial, the whole thing to the power k in order to get the right transcendental weight. And then there is a sum over m equal 1 to infinity, now with the cosine 2 pi m z, and another sum with a weighting factor n to the k minus n q to the mn, and another version which I will not completely write down, 3, 5, and follows. And this is just a sum over a sine function, no zeta value here. So I'm just paraphrasing it. You can find those functions explicitly spelled out in an article by Niels Mattes, Oliver Schlotterer, and me from 1507 if you want this particular representation, but these show up already in earlier works, for example in André Levin's paper, Elliptic Polylogarithms and Analytic Theory. They might not be in this particular language, but they do exist. Now, that's now a piece of cake. Now you have these expansions. You know that the omegas are iterated integrals over those differential forms here. So I should write it's of z and tau. Again, here z and tau. And then you can actually obtain the Q expansion. Now, you can obtain almost all of the Q expansion. Because it's an integral, we need to provide some kind of boundary condition. And we will talk about that boundary condition later again. This boundary condition is exactly the so-called constant value of the elliptic multiple zeta value. So if you have an elliptic multiple zeta value on genus 1, this constant term is an important part. And how can you actually identify that part? This part is what is left over from the from bridging the gap between genus 0 and genus 1. Saying the other way around, if we consider a certain limit of the elliptic fundamental domain, let me draw that, we might actually do take a limit of a variable and obtain the genus 0 case. So in short, if we have the elliptic domain with q equal to e to the 2 pi I tau, we'll be able to identify the piece here by taking the limit tau goes to an I infinity. What happens for tau goes to I infinity? That is equivalent to q going to 0. So if I take this limit, then the whole expansion here will vanish. And in this limit, we should better get the constant term of the elliptic multiple zeta value. What does it mean geometrically? You take tau to I infinity. That means, first of all, you make your parallelogram being a rectangle. And one can show that this is always possible and sufficient. And secondly, the rectangle will be very long, and let me put a wavy line here, so it will be infinitely long, and in practice one will take this parallelogram and let it shrink to a vertical line, which is nothing else as the integration domain of the usual multiple zeta values. So I think yesterday I drew this picture, how to degenerate the torus into a Riemann sphere by cutting it open along one of his cycles and then doing some conformal transformation and taking a limit. So the cutting is taking the limit. But this is the implementation of this procedure in the language of elliptic multiple zeta values. So this limit is called the cusp. So that's the point where you actually lose the nice differentiability and everything on your Riemann surface, because you get a cusp if you take the tau goes to I infinity limit. Those of you who are familiar with modular groups and congruent subgroups, is there anybody who knows a little about these congruent subgroups? You might then you know that these cusps are actually the quantities which determine the behavior of the modular group and appropriate subgroups completely in a certain sense. So here it is just the most easy situation, and we have the full modular group for the symmetries of the torus, and we will exclusively consider the limit tau goes to I infinity. Now, what would one do, and what did we do? We simply wrote down Q expansions and all the terms which are not the constant term we could get from these expansions of the functions G. How to get the constant term? This is something which goes under the name of the constant term procedure, and it is due to a paper from Benjamin Henriques, a French mathematician in, I think he's in Lyon or Strasbourg, I can't remember. And he showed how from a generating series of these elliptic multiple zeta values, you can take the appropriate limit on the generating series and actually get a generating series for these constant terms. This generating series he identified as the so-called Drinfeld associator. It is an object you probably have not heard about, but the Drinfeld associator is nothing else as a generating function for the usual multiple zeta values. So it is a sum over all, in a combinatorial sum over all the multiple zeta values, and there's an additional structure with the free Lie algebra in there. But let's simply stick to the fact that this is a generating series for the multiple zeta values. And because this generating series contains only multiple zeta values, one can prove that all these constant terms are usual multiple zeta values. So, as easy as it is writing three letters here, there has been an enormous effort to actually show that the degeneration of the elliptic multiple zeta values, once you take the tau goes to I infinity limit, is actually multiple zeta values and not something else, not a logarithm of 2, not a funny L number or any other thing. Good. So, examples for what? For the degeneration. I will give examples, of course. So now the tools are here. One I explained, the other one I explained only superficially. And the ways of finding that can be collected in the following statement. There is shuffle identities. And there is the Fay relations, which is the partial fraction structure on genus 1. And there's a conjecture that in the same way as for multiple zeta values, the shuffle identities and the Fay relations are able to provide all the relations in the space, and the space is again a graded algebra, conjecturally. It's a graded algebra in the same way as it is for MZVs. So the first thing you can note is that omega of n1 is minus 2 zeta n1 if n1 is even and it's 0 if n1 is odd. So if you look at the symmetries of these functions g, there is, depending on whether you look at the odd or even g, they are odd or even functions, or they have odd and even parts. And what survives only if you take a single integral over 0 to 1 will be the zeta value from the even g's. So that's the first thing. The second thing is omega of a lot of zeros, so of n zeros, is nothing else as 1 over n factorial. There's a neat statement in here, because that in turn means if you have omega 0, then this better be 1, but then we should also be able to apply that formula here. So if we demand that omega 0 is 1, or define that it is 1, then it is clear that the Riemann zeta of 0, and here really I mean the point 0, better be minus 1/2, which is exactly the value you would actually get from a zeta function regulation. So nicely, these formulae and the results for taking the iterated integrals, they match with the zeta function regularization procedure. And then one can continue and work a little more and find formulae for omega n1 and n2. There is a very simple one. If both of them are even, and there's a lot of, there's also a general formula which I won't write down for double zeta values. In short, you can basically explore the space of elliptic multiple zeta values in the same way as people did in the 19th century for the usual multiple zeta values. So there's a lot of simple, basic identities, but you can also get some more. I'll just write one complicated one. So if you have omega of 0, 1, 2, 0, this is a quarter omega 0, 3 minus 5 over 2 omega of 0, 0, 0, 3 minus zeta 3 over 4. These identities, they show a very important fact. They show that MCVs are actually elliptic multiple zeta values. So any multiple zeta value is also an elliptic multiple zeta value. So that's a statement in the same category as the one I noted up there, that the constant term is a multiple zeta value, and some of them will have no Q expansion despite of having a representation as an elliptic iterated integral, and one can prove, and that's something rather recent from 2015, that MZVs are actually elliptic multiple zeta values.
Is there a tau?
Is there what?
Is there a tau in the last equation?
Sorry, I did not understand.
Is there a tau in the last equation?
Is there a tau in the last equation? There is a tau in any of these equations.
Okay, there's constant terms.
So I'm a little lazy here, so despite of saying it numerous times, I will note the omegas just with the labels and not write the tau, because all omegas will be functions of tau. And also I should or could have provided always a letter A here, but for this lecture the letter A is understood. What you probably are referring to are so-called Laurent polynomials, and that is something we are not experiencing for the A-cycle multiple zeta values. That is a part which shows up for the B-cycle ones, and I don't want to talk about it. Now, this fey and shuffle is beautiful and analytic, but cumbersome. That is, if you want to derive these identities, you write down the integrals, you apply the Fay identity, and from writing down the Fay identity yesterday, you can already see that this is not fun. In particular, if you're going to a higher depth, so 3 integration, then you easily fill pages of pages. Of course, there is a computer implementation which does that analytically, but there's a shortcut. You could say, okay, I recognize that somehow the weight, which is the sum of the labels of these elliptic multiple zeta values, is conserved. And so if I want to find a relation, I better start with an ansatz. And then I make use of the fact that I do have a function as opposed to just a number. That is, these identities are identities which should be valid for any value of tau. And combining this with the information that we have the constant term up there and then the Q expansion, you can even choose very convenient values of tau. So what kind of values for tau you want to choose? You want your Q to be rather close to 0, because then you know that the series converges ridiculously fast. So if I get a Q which is about 100th, then the first 3 terms will already give me 3 digits on the multiple zeta value. So what is a good strategy, a numerical strategy for a quick test? I want to make sure, not a proof, just a quick test for these relations. You come up with some zeta value you want to find a relation for. You come up with an ansatz of zeta values of the same weight, not the same length. The weight is the important factor here. You write a linear ansatz because you believe that this target zeta value is just A1 times first candidate plus A2 second candidate. And then you solve a linear system. And if your ansatz is of dimension n, you want to solve the linear system for at least n plus 1 numerical points. So for each of those, you plug your numbers in the ansatz, and then you solve a numerical system. And that neatly and amazingly and very efficiently, if you choose a Q which is close enough to 0, will give you an answer. One can even make this into a proof, because secretly, these zeta values are related to modular forms. And there is a theorem which tells modular forms, they are complex functions which have a Q expansion as well. They have certain properties under transformations of the modular group. But there is a statement which tells that there's only a finite number of coefficients necessary to identify a modular form. So you don't need all the coefficients in your Q expansions, but a finite number. And there's a measure about that finite number. And that means the numerical uncertainty is even bounded from above. That is, you can get away with a finite number of linear equations for identifying these relations between the zeta values. Now, what is a good example? Just to write it down, if you take tau equal to IT, so purely imaginary, equal to I times 0.8, then you already get that 1 over e to the 2 pi times 0.8 is something like 0.0056. So that is an amazingly efficient Q for a Q expansion. Already Q cubed will give you something only on the 5th or 6th digit. So you can basically get amazingly fast convergence here. So the whole the whole set of relations has been collected on a web page, which is the chance for me to also mention another web page. So relations between usual multiple zeta values are available in something called the MZV data mine. And this is something from the end of the 90s. I think it's 98 or 99. It has been calculated by Blümlein, Broadhurst, and Vermaseren, and was one of the main applications of the not computer algebra system. He doesn't call it like that, but I think it is, form. So Jos Vermaseren, Dutch physicist, has come up with an alternative to Mathematica, which is programmed in C. It has an amazing pattern matching system which exceeds even the Mathematica abilities and is very much suitable for doing experiments, analytic experiments, no numerical experiments with multiple zeta values. And that has been a paper which has been, for various reasons, referenced extensively because most of the people actually used the relations in there. So that's it's a web page. You can find it by Googling for MZVs. And there's an analog which is for elliptic multiple zeta values. And I think I wrote down, yes, here it is, the web page. It's at tools.aei, which is the address for the Albert Einstein Institute, .mpg for Max Planck Society.de/EMZV. And in there, you can download all relations up to a certain weight and up to a certain length for elliptic multiple zeta values. So there is a source which actually gives you all relations and identifies a suitable basis for these elliptic multiple zeta values. This basis is an heuristic basis or an empiric basis. It is based on selecting the shortest and well-ordered zetas. That is, one wants as many zeros as possible in the beginning, as little as possible n's which are not zero, and you can come up with a couple of things. I will write down a table later during this lecture, but this is a source if you want to play around with those numbers. And one can even, for low length, so you have a weight grading. For the length, it is not a grading, but it's just to label the length. For low length, you can even identify formulae similar to the to SAGEX conjecture for the dimension of multiple zeta values for a certain weight. Okay, are there any questions so far? Good. So one thing we didn't yet talk about was regularization. For the usual zeta values, I explained that one has endpoint singularities, and these endpoint singularities, they can be removed by defining certain quantities, in particular divergent quantities, to be zero, and that can be done in a way which preserves the shuffle algebra. And the same is true for the elliptic multiple zeta values. Now here, the situation is a little different. So we are looking at the interval from, so the integration interval from 0 to 1. So I'm drawing the lower line of the fundamental domain here, but these two sides are identified. That is, if the function g1 has a pole at 0, it will also have a pole at 1, at 2, and so on. Now, something we will get definitely an endpoint singularity when we approach z equals 0. Up there you can see the cotangent, and the cotangent, I said it already, behaves like 1 over z the closer you get to z equals 0, but the same will happen for z equals 1. The idea is that one has to sort out which direction one actually approaches the pole, and I think it was a question yesterday after the lecture how to do that consistently. The answer is the concept of tangential base point regularization, and the easiest approach for doing so is to consider an iterated integral. There's a squiggle now above the gamma, which means that we have one which is with respect to the real line, so that's exactly what you know and want, and you want to consider how to regulate this particular function. So it's the only thing which can get you into trouble once you approach 0 and 1. Yes?
So just now that you said that the cotangents would also diverge at 1, shouldn't cotangents 2 pi then?
No. It's pi cotangent of z, and maybe it's cotangent of pi z.
This is cotangents of pi.
Yes, thanks. That's. Let me show whether I mistyped yesterday or not. I did. It's yeah. Thanks. Yeah, that is an important ingredient here. So sorting out the regulation of these gamma tilde reg, which is just the integral over G1, is a nifty business. You have to carefully select where you put the branch count of the logarithm, and you can derive things like gamma tilde regulated is 1, 0 of z plus minus 1 of z plus minus 1 and tau. This is nothing else as the regulated integral at 1, 0 z and tau minus plus I pi. So in short, you will get correction factors of pi I, which correspond to half a circle if you demand that you approach the limit always from the correct direction. So yesterday, answering your question, I drew a picture like approaching a point and then having half a circle in order to approach it from the correct direction. That will explain precisely these factors of I pi, which you need to add or subtract depending on which direction you're actually taking your period here, whether it's +1 or whether it's -1. There is numerous references. There's the mathematical papers. There is a very short account in Enrique's papers how to regulate these things. There is a long explanation in Francis Brown's modular values paper, which is difficult to read, for me at least. And there's a explanation in the paper Amplitude Recursions for an Extra Marked Point from December from Andre and me, where this is explained in detail. Now, what does it mean for the... one word more. In the same way as you could shuffle out all the zetas with 1, all the divergent zetas in the MZV case, you can do the same thing here. So that's the analog of zeta of 1, or 1 with the letter 1, and you will do precisely the same thing, and whenever you encounter one of these regulated 1, 0 for the polylogs, you will shuffle them out because that's a behavior you can control. And you will do exactly the same for multiple zeta values. So the omega A regulated multiple zeta value of n1 to nr of tau is either omega of n1 to nr as long as n1 is not equal to 1 and 0 for all the n1 to nr equal to 1. And all other cases can be taken care of by shuffling. And from now on, I will only talk about the regulated version of these elliptic multiple zeta values in the same way as I did for the genus 0 situation. Shall we have a break for 5 minutes? That's a good point. I need to wipe the blackboard anyway. So 5-minute break, please. Can you ask you at the beginning of the next? Good.